In life, as with fluid mechanics, it's oftentimes good to take the path of least resistance. So here I have a network of straws. The network of straws is connected to a reservoir of water up here that we're going to fill up with water in just a sec. So we can see two outlets for the straws, one connected to a short straw and one to a long straw. So take a moment now, pause the video, and observe which flow out of which end of the straw is going to have the higher flow rate. Okay. All right, so we observe two flow rates. Well, I think just visually one is much higher than the other, but we can see how quickly they each fill up their respective cups. All right, so our race is complete, and we can see that the yellow cup gets completely full, whereas the red cup maybe even filled about a third of it full. So the path length, or as we'll anticipate in just a second, the hydraulic resistance of the branch of the flow makes a huge difference in terms of the flow rate that we observe at the end. So what's the plan to explain this phenomenon? Well, first we're going to talk about the origins for how we can build a model for explaining this behavior of the differing flow rates from the two outlets. And it turns out that one route that we can start with is essentially a simplification of conservation of energy. Of conservation of energy, aka the engineering Bernoulli, plus a few additional assumptions that basically enable us to get rid of a handful of terms in conservation of energy to keep the essential parts that really model and explain this behavior. And in doing so, we'll basically make a connection between a pressure drop in pipes and viscous losses due to flow through those pipes. So we'll basically make this connection via conservation of energy. Then we'll take a step back and talk about the idea of a fluidic resistor. Or sometimes people call them hydraulic resistors. And basically how it's a connection, it's something that we could sort of treat, and it turns out it has analogies to electrical engineering. We can basically relate pressure drops to volumetric flow rates through a fluidic resistance or a hydraulic resistance. Building upon this idea, this connection to, or this analogy to electrical engineering, we'll talk about tubes in series and tubes in parallel. Similar to how you might talk about electrical resistors in series and electrical resistors in parallel. How can you combine them? How is pressure drops analogous to voltage drops? How is electrical current analogous to volumetric flow rate? How do we sort of combine resistances in series and parallel? And once we sort of set up this framework for the fluidic resistor analogy, we'll work through an example problem that involves fluidic resistors. And it's basically the design of a bioreactor, or the design of a component in a bioreactor. So it's the design of a tubing system in a bioreactor, and with the goal of balancing flow rates to two separate growth chambers. So that's the plan. So here's the plan here. So let's talk about conservation of energy and how a few simplifying assumptions can kind of pull out some parts of conservation of energy that turn out to be useful in most cases. So if we put down the full conservation of energy, we have the following equation. We have W dot S, which was the shaft work, the power sort of extracted from our system by a turbine, or the negative of any power put into our system for a pump, divided by little w, which is the mass flow rate. Then we have this viscous loss per unit mass term, which essentially accounts for all of the turbulence or friction or viscous effects of trying to pump flow through pipes. And this is equal to 1/2 times this V in over V in. This bracketed thing was sort of an average over the cross section. So this is essentially the kinetic energy in to our system and the kinetic energy out of our system. And then we have G times H in minus H out. And then, and this is the potential energy change of our system. And then we have 1 over rho H in minus H out. And this is the, P in minus P out. And this is essentially the pressure at the inlet and the pressure at the outlet. So we basically have all of these terms here. Essentially, these terms are related to work. This is friction lost in our system. This is kinetic energy. This is potential energy. And we might have some problems, for example, that bottle draining problem that we talked about earlier, where all or many of these terms come into play. But, and even to use this equation in the first place, we must assume steady, incompressible, homogeneous fluid, i.e. density is equal to a constant. We also must assume we have a single inlet and single outlet in our system there. So a fair number. Oh, and that we're isothermal as well. So this certainly restricts the applicability, but this is still a general enough equation where it ends up being pretty useful. A lot of times in systems, particularly networks of tubes or networks of pipes, for example, like all of the blood vessels in my body, or microfluidic channels, like arrays of microfluidic channels, or things like that. A lot of times in systems like that, we only need a subset of these terms. So a lot of times for certain systems, often we have no pumps within the control volume that we define for the system. Maybe we have some pump upstream that's sort of generating pressure in some way or something like that. But a lot of times we might choose our control volume in such a way that the pump is sort of external to our system. So we don't have any pumps sort of within our control volume. A lot of times the velocity profile at the inlet is the same as the outlet. So for example, if I have a pipe with some diameter here, and the pipe has the same diameter here as here, a lot of times, unless we have some weird entrance effects, we have the same velocity profile here as here at various points in the flow. And a lot of times we have systems that are sufficiently horizontal. as to neglect the sort of the potential energy term here. Right, so a lot of times we have a certain set of systems where these assumptions apply. So it turns out that if we have no pumps within the control volume, we can basically get rid of the term in conservation of energy that's associated with pumps. If we have a velocity profile that's the same as the inlet, same at the inlet as the outlet, we don't actually really need to explicitly solve for what these kinetic energy terms are. As long as the velocity profile is the same in both, we have the same kinetic energy going in as going out, so there's no change in kinetic energy from the inlet to the outlet. So we can end up getting rid of this term as well. And then a lot of times in bioengineering systems, where we sort of have like some system and it's like all the tubes are all arranged on the table, so our system is horizontal, and in that case we can get rid of this term right here. So if we these are some of the most frequent conditions, or the most frequent assumptions that might crop up in bioengineering systems, and this allows us to make considerable simplifications to this steady state energy right here. One additional thing is we can typically, when we're looking at this viscous loss term, if you remember, a lot of times for viscous losses, we had a viscous loss that was associated with the flow through a pipe, but we also had kind of other effects like bends and expansions and contractions and like half-closed valves and things like that. So if you neglect, if you sort of assume that all of the viscous losses come from this sort of long pipe effect, then you can basically just put in one relatively simple term for this viscous loss term right here. So let's explore the implication of that, right? So if we have all of our viscous losses essentially coming from this long pipe effect, we can sub in one particular expression for this viscous loss term. So when we make this this particular substitution for all of the viscous losses coming from this long pipe effect, if we make that long pipe effect substitution right here, we end up with 4 times the friction factor times the length of the tube divided by the hydraulic diameter of the tube times 1/2 the average velocity in the tube squared is equal to 1 over rho times the pressure at our inlet minus the pressure at our outlet. And if we make one additional assumption, that the flow is laminar, again, not always the case, but very often the case, if we have the flow is laminar and the tube is circular cross-section, then we basically have an expression that we can sub in. If we have laminar flow in a circular tube, we have a pretty straightforward expression that we can sub in for that friction factor. And it appears to be the following. So for laminar flow and the tube is circular, the 4 times the friction factor is equal to 64 over the Reynolds number based on D. So this is basically 64 over density times average velocity times the diameter of the tube divided by viscosity. Well, we can take this and we can plug that in here, and we're looking to basically more closely relate pressures to flow velocities, or in particular, and which will then be able to work out towards pressure in terms of volumetric flow rates, which is sort of what we care about. So we can make this substitution. So we have 64 mu over rho v d times
times L over D. And in this case, for a circular tube, the hydraulic diameter is just the diameter of the tube. And then we have times 1/2 average velocity squared is equal to 1 over rho times P in minus P out. We can further simplify things by noticing that some terms cancel out. So the velocity in the denominator here cancels with one of those velocities here. The 1 over rho on this side can cancel with the 1 over rho on that side. So what are we left with? Well, we're left with 32 mu times L over D squared times the average velocity is equal to P in minus P out for basically laminar flow through a circular pipe where all the viscous losses come from this. The thing is horizontal, the velocity profile at the inlet and outlet is the same, and we have no pumps. And all of these assumptions that I went into here, right? And I know this is a pretty hefty list of assumptions, but it comes up all the time, or at least close enough in fluid mechanics, where we can basically say, hey, in this case, the pressure drop is basically proportional to the velocity and some geometrical factors that are pretty straightforward to measure. One last thing that we like to do is, average velocities are sometimes useful, but a lot of times, particularly for like microfluidics or, considering like parts pumping blood around the body, or bioreactors where we're pumping flow to various parts of the system, it's not actually the average velocity that we care about a lot of times for our engineering use. It's basically how much fluid am I pumping per unit time, in which case we care about volumetric flow rates. So a lot of times when we care about volumetric flow rates, it's useful just to do one more tweak on this equation where we basically say, hey, this average velocity is essentially equal to the volumetric flow rate divided by the cross-sectional area, or in this case, the volumetric flow rate divided by pi over 4 d squared, or 4 times the volumetric flow rate divided by pi d squared. So let's take this average velocity, we'll sub it in here. This is essentially the definition of average velocity. We can sub that in here, so we can basically say the pressure at the inlet minus the pressure at the outlet is equal to the following: 128 over pi times mu times L over d to the 4th, where we have a d squared in the denominator here, and we already had a d squared here, so that's why we have d to the 4th in the denominator here, times the volumetric flow rate. And this is a result that is going to be super useful. So what's the key takeaway? In systems where we have this somewhat restrictive but generally pretty useful set of assumptions, we have this result here where pressure drop is proportional to flow rate. And the proportionality constant is this collection of terms out front right here. Pressure drop is proportional to flow rate, and the proportionality constant is basically things that are pretty easy to look up. I can, if I know what fluid I'm dealing with, I can go online and I can say, hey, what's the viscosity of water? What's the viscosity of honey? What's the viscosity of air, right? I can basically plug in, any viscosity I care to look up. And the length and diameters of tubings are very easy to formulate. I can take out a pair of calipers, a ruler, a meter stick, whatever, and I can measure lengths and I can measure diameters. So this proportionality constant is basically constants that are easy to measure or look up or whatever. So in this case, I kind of group all the constants, the things that are easy to measure, I can kind of group them together into one collection of terms. And this collection of terms for flow through these circular pipes basically serves as the proportionality constant between pressure drop across those pipes and volumetric flow rate through those pipes. We call this collection of constants the hydraulic resistance. So this collection of constants is what I call the fluidic, or sometimes hydraulic, resistance. And I'll call it R sub F, the F indicating that it's a fluidic resistance, and the capital R indicating that it's a resistance like a resistor. And in the context of this class, I'm going to give hydraulic resistances a sort of double bar over here on the left. And this is to sort of contrast it from this. So this hydraulic resistance is I'm going to use this sort of weird looking R to denote that, to basically distinguish it from capital R, which would be like the radius of some pipe, or little r, which would be like a coordinate, like a coordinate in like describing the position, the radial position of some point like here. So we have a handful of r's floating around. In this case, this hydraulic resistance is what I'm using for this capital R right here. So take a moment now, pause and ponder. What are the units of hydraulic resistance? So let's work out the units. Well, the 128 and pi don't have any units, but viscosity has units of kilograms per meter second. Length has units of meters, and diameter to the fourth would have units of meters to the fourth. So how does that all work out? Well, this meters cancels with that meters, and we end up with something that has units of kilograms per second times meter to the fourth. I'm going to be honest, this is not particularly intuitive or particularly helpful. Instead, I'd like to offer an alternative way to think about the units. On the left-hand side, we're basically going to have pressures, which are going to have units of pascals. On the right-hand side, we're going to have units of volumetric flow rate, which is going to have meters cubed per second. So when I think about the units of my constant right here, I would like to think of this as having units of pascals per meter cubed per second. And just to basically say, it's to sort of reinforce the idea that it's this proportionality constant right there. So a lot of times you might find these hydraulic resistances expressed in terms of a pressure per flow rate rather than the base SI units, which are kind of confusing and don't necessarily really lead to physical intuitions about the system. So what's the key takeaway here? The key takeaway here is that pressure at the inlet minus pressure at the outlet is equal to the fluidic resistance of the particular tube with the particular fluid that's in it times the volumetric flow rate of that fluid that's in it. And it turns out that we can extend this idea of fluidic resistances. This can extend to non-circular geometries. But if you extend it to non-circular geometries, you basically need to use a different formula than this one for the fluidic resistance, which essentially, this is equal to the fluidic resistance for a circular for a circular cross section. So it turns out you can extend this to non-circular geometries. For example, a lot of people in microfluidics care very deeply about rectangular cross-section channels, because those rectangular geometries are easier to emboss in microfluidics. But anyway, I digress. Pressure drop is proportional to volumetric flow rate, and fluidic resistance is the proportionality constant. So that's the key takeaway here. So let's go back to our plan for the day. we made a simplification to conservation of energy with a few additional assumptions, and we basically said, hey, pressure drop is basically related to viscous losses. We then brought in the idea of a fluidic or hydraulic resistance, which basically said pressure drop is proportional to flow rate, with this proportionality constant of the fluidic resistance serving as the relationship between the two. It turns out that you can actually derive this relationship. You can actually derive this whole relationship right here. You can get this via, instead of conservation of energy, you can actually get here via conservation of momentum. And I have a derivation of that in the lecture notes that I've posted online, but it's a cool and interesting problem, but I really don't think it's necessarily worth devoting a whole 10 or 15 minutes in order to derive that as well. This, I think, serves our intuitions just fine, and using this result is really what I'm interested in terms of moving forward. So now let's talk about this idea of tubes in series, tubes in parallel, and we'll preface this with an analogy to electrical engineering. So let's do that. So in electrical engineering, we'll build a little chart. In electrical engineering versus bioengineering. In electrical engineering, we talk about flow through voltage drops, electrical current, and resistors. So we think of in electrical engineering, we think of voltage as the thing that drives the flow. So in this case, the voltage drop is the thing that drives electrical current through resistors. And in bioengineering, aka fluids, we might talk about a pressure drop as the thing that drives the flow. In electrical engineering, we talk about an electrical resistor. And in bioengineering, we talk about fluidic resistors. In electrical engineering, we talk about electrical current. And in bioengineering, we talk about a volumetric flow rate. So these things are essentially analogous to each other. So in electrical engineering, we use Ohm's law. Ohm's law. It's not Ohm's law like Cold's law. It's Ohm's law, which basically is saying that V, the voltage drop across a resistor, is proportional to the current through that resistor times its electrical resistance. And in this case, in bioengineering, the pressure drop across a fluidic resistor is equal to the volumetric flow rate times the fluidic resistance of that system. And we can basically, these analogies hold. Similarly, in electrical engineering, we had Kirchhoff's current law, where if you had, for example, a couple of resistors going into a node, and you had some currents going in and some currents going out. For example, let's say I1, I2, and I3. Then the currents in need to equal the currents out, because we essentially can't have storage of current at sort of a point that they're all connected. So basically, I1 plus I2 is equal to I3, Kirchhoff's current law. And in bioengineering, well, the analogous term in this case is conservation of mass, where we've basically taken conservation of mass and multiplied it by 1 over density, which essentially is a balance of volumetric flow rates in and out. So if I have, for example, like a couple of tubes where I have some let's say 2 volumetric flow rates in and 1 volumetric flow rate out. This is analogous as well, right? So conservation of mass is kind of the same as Kirchhoff's current law. The hydraulic resistor or fluidic resistor relationship is the same as Ohm's law, and pressure drop, voltage drop are analogous. Fluidic resistors are analogous to electrical resistors, and volumetric flow rate is analogous to electrical current. So with thinking about when if you approached electrical engineering, you might have had these problems where you had networks of circuits and currents were flowing through various things and voltages were across them, but you were able to sort of simplify elements by sort of combining things in parallel or series to come up with equivalent resistances. And it turns out you can kind of do the same thing with fluidic circuits, where you basically have networks of tubes with fluids flowing through all of them. So let's talk about tubes in series and tubes in parallel. So let's do tubes in series first. So by tubes in series, let's say I had one tube, let's say a small tube of some particular length and some particular cross section, and then that was connected to a larger tube right here. So I have 2 tubes, they're connected to one another. Let's say I have some pressure at the inlet, and I have some pressure at the outlet. And if I have these 2 tubes connected to one another, let's say there's some volumetric flow rate through one. What could I say about the volumetric flow rate through this other one? Perhaps pause and ponder. What can I say about this volumetric flow rate right here? Well, if I have some fluid coming in here and some fluid going through there, the volumetric flow rates for these 2 things must be the same, right? They if I had some volumetric flow rate that was different here from here, I'd be sort of building up extra fluid at some somewhere in the junction, which I'm saying doesn't occur for these systems that kind of remain rigid in this way. So we have this essentially the same volumetric flow rate. So this idea of tubes in series, we can basically say the QV is the same for both, but the pressure drop across one might be different from the pressure drop across the other. So we can basically say, hey, we might have some pressure at the inlet, we might have some pressure at the outlet. There's going to be some pressure at the middle point that isn't necessarily half here and half here, right? So the pressure drop across one and the pressure drop across the other sort of need to be the same as the pressure drop over them entirely, but the pressure isn't necessarily divided evenly. So volumetric flow rate is the same for both, but pressure drop not necessarily shared or divided evenly. And in fact, the drop is sort of proportional to the 2 resistances that exist. So so a lot of times we might say, hey, if there was some fluidic resistor of this from this first section and some fluidic resistance of the second section, could I come up with some equivalent resistance, without sort of needing to say, okay, without sort of bringing in this, this middle pressure and kind of complicating things, could I basically say, hey, is this equivalent to some system that has some fluidic resistance, some equivalent fluidic resistance to the whole system that basically would give an equivalent P in, P out for a particular volumetric flow rate that's the same. So that's the idea of combining tubes in series, and you can basically formulate that by basically looking at this one and looking at this one and adding them up and trying to make it equivalent to this thing. So we can basically say, hey, let's apply this relationship to the first resistance. So that's basically going to be P in minus P mid, because if I look at the first one in isolation, mid is essentially the outlet of the in, or the outlet of the first tube. So that's basically going to be the fluidic resistance of 1 times the volumetric flow rate. And then if I look at this other one, mid is now the inlet for the second tube. So it's basically P mid minus P out is equal to the fluidic resistance of the second one times the volumetric flow rate. I can take these two equations and add them, and the P mids essentially cancel out because I have minus P mid in the first one and positive in the second. So I end up with P in minus P out is equal to, they both have a volumetric flow rate, so I essentially can factor that out, and I end up with the fluidic resistance of 1 plus the fluidic resistance of the second one times the volumetric flow rate. Or equivalently, I could say that this is equal to some equivalent resistance of the resistor 1 and 2 times the volumetric flow rate through the system. So what is this saying? This is basically saying that if you combine tubes in series, their fluidic resistances add up to give you the equivalent resistance. And that this makes sense to us, right? If I take some tube and essentially make that system much longer, then it's going to require more pressure to drive the equivalent volumetric flow rate. So tubes in series, you add the fluidic resistances to get an equivalent resistance. So what's the next step? Well, we talked about tubes in series. Now let's talk about tubes in parallel. So for tubes in parallel, what might a system look like? Well, I might have some common inlet that then branches into two separate sections that then perhaps recombine later on. And what might those branches look like? Well, those branches don't necessarily need to be the same as each other, right? I could have some skinny branch on one side and some real thick branch on the other side. I basically have some volumetric flow rate that maybe I'll say is the total going through the whole system, and whatever comes in must come out right here. And let's say I have some pressure at my inlet, P in, and some pressure at my outlet, P out. And if I just looked at one part of the branch, essentially, regardless of which branch I look at, if I look at this branch or look at this branch, the pressure drop, if these two tubes are in parallel, the pressure drop across the two is the same. So for tubes in parallel, so the pressure drop is the same for both, but the total volumetric flow rate is essentially split between the two, and it potentially is split unevenly. So the volumetric flow rate is split between the two, and it's potentially split unevenly. So if it's split unevenly, let's say I have some volumetric 1 going down branch 1, and then some volumetric flow rate 2 that goes down branch 2. So and then let's say that there's some fluidic resistance for branch 1 and some fluidic resistance for branch 2 as well. I might ask, is there some if I don't really care about the details of how the split occurs, if I just want to say, hey, this branch, these two branches in parallel that then recombine later, could I say that this is equivalent to just having a single tube where there's some equivalent fluidic resistance that has the total volumetric flow rate that just goes through and also has a P in and a P out that is the same, right? So could I basically say, hey, if I didn't care about the details of how the split happened, if I just care about the relationship between volumetric flow rate and the pressure drop, could I essentially take these two fluidic resistances and express them in terms of an equivalent resistance that gives the same result? So let's see if we can work out an expression for this equivalent fluidic resistance. Well, I can apply essentially I can apply Ohm's law. I can apply Ohm's law for fluid mechanics to each of the branches separately. So Ohm's law So I can apply Ohm's law for fluids to each branch. So what would that look like? That would basically say P in minus P out is equal to the fluidic resistance for number 1 times its volumetric flow rate. And P in minus P out for branch 2 is equal to its fluidic resistance times that branch's volumetric flow rate. And this is an okay start, but it turns out to be helpful if we divide the fluidic resistances to sort of bring them over to the left-hand side. So let's do that. So for this equation, P in minus P out divided by the fluidic resistance for number 1 is equal to the volumetric flow rate for number 1. And if I do the same thing for this one, P in minus P out over the fluidic resistance for number 2 is equal to its volumetric flow rate. If I then take these two results and add them, what do I get? I get P in minus P out times, well, both of these terms have a P in minus P out, so I get 1 over the fluidic resistance for number 1 plus 1 over the fluidic resistance for number 2, and that's equal to QV1 plus QV2, the two volumetric flow rates. And if you remember, I said, hey, the total volumetric flow rate is split into these two branches. So these two branches must add up to the total volumetric flow rate, applying the conservation of mass, essentially applying conservation of mass to this part of the branch. So what does this mean? P in minus P out. Well, we can sort of replace this with QV total, and then we can divide both sides of the equation by this right here. So we end up with fluidic resistance for 1 plus 1 over fluidic resistance for number 2 to the minus 1 times QV total. So in this case, this expression right here is our equivalent resistance that we're going for. So this is the equivalent resistance for parallel pipes, in contrast to when we had pipes in series. So if you have for pipes in series, the equivalent resistance is adding them up. When you have pipes in parallel, the equivalent resistance is taking the inverses and then summing up the inverses and then inversing that. If you have just two resistors, if you have two resistors in parallel, the equivalent resistance for for parallel ends up being R1 times R2 divided by R1 plus R2. So basically that equals 1 over R1 plus 1 over R2 to the minus 1. These two things are basically equivalent to one another. It's sort of like the product over the sum. But the key thing to watch out here is this simplification here only works for 2 in parallel. If you have 3 in parallel, you don't get the product of all 3 things over the sum of all 3 things, because the units wouldn't even work out in that case. And these are basically the same rules for electrical engineering circuits. We have the thing in parallel, the parallel rule. We have the series rule, and it works for both electrical engineering and for fluid mechanics. So, with that in mind, we now have rules for how to combine things in series and parallel and in analogies to electrical engineering. And you can imagine just plopping down some quick formulas like this, especially if we have a straightforward way to calculate what these fluidic resistances are for circular tubes. You can imagine this is going to be a heck of a lot easier than applying this whole messy, than starting from conservation of energy or engineering Bernoulli every time. You can imagine, oh my goodness, if I asked you to start from engineering Bernoulli for every problem, and you can imagine if we had huge, vast networks of tubes and all that stuff, you would just say, Professor Lannin, seriously, you're going to make us do this? But we can sort of take into account all of these assumptions, arrive at fluidic resistances, apply some analogies to electrical engineering, and then use some shortcuts for parallel and series resistors to get to some results pretty quickly. So with this accelerated approach in mind, let's now proceed with doing an example problem. Where we're looking to design a tubing system to balance flow rates to do two different chambers where we're growing cells. So let's get started on this example problem. Imagine I have the following system. So let's say I have some network of tubes that are from some syringe pump source and that are delivering cell culture medium to 2 growth chambers. So there's a sort of network of tubes right here, and they're the sort of culture flasks that are sort of exposed to atmosphere. At the end, there's culture medium in them, and there are a bunch of cells kind of happily growing in there. So let's say I knew the following about this system. I knew what volumetric flow rate I was pumping into the whole system like this. Let's say I wanted 2 particular volumetric flow rates out. So let's say I basically wanted half of the flow rate to go to this one and half of the flow rate to go to the other one. So let's say I basically wanted this to be 1/2 Q in and this one to be 1/2 Q in. I think I'll neglect putting the V in just to make things a little bit less encumbered. But these Q's are volumetric flow rates in the context of this problem right here. Right, so let's say basically I had some Q in and wanted half to go to each of these. So we can see that this essentially obeys conservation of mass here. And let's say I knew the diameter of these 2 parts of the tubing. So both of these tubes have some diameter d naught, and all of these segments have length L. So all the segments of the tube have length L, but the tricky thing here is we basically have two diameters. I'll call D1 right here and D2 right here, and it's up to us to basically say, hey, for this particular volumetric flow rate right here, and this particular prescribed inlet pressure, P in, if I have some prescribed inlet pressure, some prescribed volumetric flow rate in, and the rest of the geometry of this system well defined, can I find two diameters that basically perfectly balance the flow to these two chambers here? So in a sense, this is the opposite of the demo that we showed earlier, where we had a short leg and a long leg, and we noticed that we got imbalanced flows between them, right? The short leg stole most of the flow, whereas the long leg only got a fraction of it. We're saying, hey, could I go back? Could I get a new demo where I tweaked the diameters of these two such that even though one of the segments was longer, I balanced the flow rates for the outlets? So this is our goal. So I'm going to model this system as a resistor network where I have one resistor for this first segment here, some node right here, another resistor, a resistor for this segment right here, a resistor for this segment right here, a resistor for this segment right here. And in a sense, because both of the outlets of these tubes are essentially connected to, they're both exposed to atmospheric pressure out here, in a sense, these two are, the ends of these two resistors are essentially connected to each other, because those 2 points are essentially at the same pressure in this circuit, or if we were kind of viewing the electrical engineering analogy, they'd be at the same voltage, which is equivalent to them being connected. So here we have it. We basically have resistances of the various segments. So I'm going to call the fluidic resistance of this segment, I'm going to call it R naught. And if we notice, we have the same diameter and length here as here. So this segment is also going to have a fluidic resistance R naught. There's also some fluidic resistance for this segment right here, and I'm going to call this one R1, and there's a fluidic resistance for this segment here, which I'll call R2. So we have R naughts for these ones, R1 and R2 for these, and if we think about it, the equation for any fluidic resistance, if we're assuming circular cross sections, so if we're assuming a whole list of assumptions that we need to make, we're assuming we're in steady state. We're assuming we're in steady state. We have laminar flow through all of these. We're assuming we have laminar flow through all of these tubes, which would be pretty good, unless we're really blasting this cell culture medium. Laminar flow would be a pretty good, probably be a pretty good assumption. We're assuming we're isothermal. We're assuming we're horizontal, and we're assuming that we have a constant density. Because we're sort of assuming some viscosity of the fluid kind of implicitly in these hydraulic resistances, we're assuming we have Newtonian fluid. We're basically assuming, we know that this system is going to need some pump to drive it, but the pump is somewhere upstream of this part of our system right here. So we basically have no pumps or turbines. And, strictly speaking, we have some kinetic energy of the fluid coming in and some kinetic energy of the fluid going out, but we're going to basically neglect the kinetic energy change of our fluid. And if we do all that, we can basically this justifies the use of fluidic resistances. And in this case, we have these circular cross sections. The fluidic resistance is 128 times mu times L over d to the fourth. So we can basically formulate it for each of these ones. So in this case, R naught is 128. We're assuming we know the viscosity. We're assuming we know the viscosity of the fluid flowing through these pipes. So mu, and in this case, I have a sort of L in general right here, but we can sub in the particular length L, which we're treating as a known constant in this situation. And for the resistances associated with these R naughts, it's basically going to be D naught to the fourth. So what does that mean? We can basically treat R naught as a known constant because we could put it in terms of all of these known constants right here. We can similarly form resistances for R1, which is going to be 128 mu L over D1 to the fourth. So I'm just going to treat R1 as an unknown constant in the time being. And once we find what we need for R1, it'll be pretty straightforward to find D1, or vice versa. Similarly, R2 is related to D2 to the fourth in the denominator here, and 128 mu L over the top. So what does this mean? R2 is basically also an unknown because D2 is unknown. So we have this R2 D2 phenomenon going on. So what's the deal? We have sort of two unknowns in our system. So we're going to need at least two equations to help resolve these unknowns. So we'll try to put two unknowns in terms of some of the rest of the knowns of our system. So for example, we'll try to put R1 and R2 in terms of R naughts, as well as in terms of Pn and Qn, and some of that stuff that's going on here. Oh, I'm just looking back at my notes. I had the wrong formula right here. I forgot pi. How could you forget the pi? How could you possibly forget pi? So I have pi in all these denominators right here. Whew, whew, don't forget the pi. Okay, so what does this mean? We now basically need to proceed with formulating at least two equations to try to relate these unknowns. So if I think about it, I have some volumetric flow rate right here, and I know volumetric flow rates through these. So, can I relate? And I also know I know P in and essentially P out. If we work in gauge pressures, we can say is 0, right? So what does this mean? Hopefully, using this idea of maybe combining things in parallel and series, I can eventually work towards a set of equations where I can have at least two equations where I can have R1 and R2 in there. So don't get mad at me. I'm going to throw in one additional unknown, which is basically the pressure at this point right here. And I'm just going to call it the pressure at point A. So let's just call point A this node right here. I'm going to throw in pressure at point A as some intermediate unknown variable. And it turns out that, I'm basically going to relate some of these things to PA and eventually get back to PN. So even though I'm throwing in another unknown, it'll help us get a couple of extra equations that will be a little more intuitive to help solve this system here. So let's apply Ohm's law to this branch right here. So when we do that, we end up with, let's carve ourselves out a little bit of workspace right here. So let's apply Ohm's law to this branch. So pressure right here minus pressure right here, which is 0. So we're going to get PA minus 0 must be equal to the volumetric flow rate through this times R1. We can also apply Ohm's law to this branch right here, noting that these two are in series. So these are in series, where their equivalent resistance would be the sum of those two resistances. So what does this mean? PA minus 0 is also going to be equal to the sum of these two resistances times the flow rate through this branch. It's basically saying Ohm's law applies here. Ohm's law also applies to these two if I combine them into some equivalent resistance. So what does that look like? We basically have the sum of these two resistances as their equivalent resistance, R0 plus R2 times the flow rate through this branch, Qn, or sorry, 1/2 Qn. So now we have two equations. They're both equal to PA minus 0, so we can essentially set them equal to each other. So we take these two, set them equal to one another, and we end up with 1/2 Qn must be equal to, 1/2 Qn times R1 must be equal to 1/2 Qn times R0 plus R2. If we notice both of these, both sides of this equation has a 1/2 Qn, so we can just divide that out, and we basically see that R1 needs to be equal to R2 plus R0. So awesome. This is, so we anticipated we had two unknowns. We now have one equation relating these, so we're going to need another equation trying to relate these two, preferably roping in some of the other known parameters in this system. So what's the plan for doing that? If I could take this entire circuit, and replace it with some equivalent resistance for the entire circuit, then I could basically say, hey, Pn and Qn relate to the equivalent resistance for this entire circuit. And if I had an equivalent resistance for this entire circuit, that would probably have R1 and R2 kind of built into it. So if I can have, so that's basically going to be where my final equation comes in. If I take this entire system, this entire network of resistances, and replace it with some equivalent resistance, R1 and R2 are going to be built into that equivalent resistance, and then I can incorporate these other two knowns. And that will give me a second equation, and between that second equation and this one, I'll be able to solve for the unknown R1 and R2, which then you can imagine I could just plug straight in here and get my as of yet unknown diameters for it. So that's the plan. So let's try to march through this system here, combining resistors in series and parallel to get some equivalent resistance for this entire circuit, to get that second equation that we're really going to need. So let's proceed with doing that. So in a sense, we already kind of dealt with one of these branches here. So this whole network that we had here is equivalent to So this network right here is equivalent to this network right here, where we still have R0 right here. We still have R1 right here, but we said we took these two and combined them in series and replaced them with some equivalent resistance right here. The equivalent resistance right here is basically R2 plus R0, where we basically combined these two resistances right here into an equivalent resistance for this branch. Now, if we look at these two branches right here, these are in parallel. So if I treat this as kind of some unit here, I can say that these two in parallel, that this whole thing, combining these two in parallel is going to be equivalent to this resistance here. I haven't touched this top one, this top R0 here, but if I take two resistances and combine them in parallel, then the equivalent resistance for these two resistors, one of which is already an equivalent resistance, is the product over the sum. So I'm going to have R1 times R2 plus R0 sorry, I forgot my subscript 1 right here, R1. It's the product, right? This resistance times this resistance over the sum, which would be this resistance plus this resistance. So it would be R1 plus R2 plus R0 is this equivalent resistance. Then I can say this right here, this system is equivalent to these two in series. So what is this? This is basically equivalent to a single resistance. And this single equivalent resistance for the overall system is basically the sum of these two. So what does that look like? We get an R0 for this thing here plus this term that we brought down right here. So what does this mean? We now have an equivalent resistance overall, and if you remember, an equivalent resistance is basically, so if we look back here, we have P in right here, and 0 pressure right here, and the flow rate is Q in. So we can basically say, hey, we can reformulate Ohm's law, where we basically say P in over Q in is now equal to our equivalent resistance overall, where I just basically brought QV, our volumetric flow rate, over to this side, and that's equal to this right here. So what does this mean? We now have one equation here and another equation here. So we have two equations and two unknowns. So we can solve that algebraically. So how do we go about actually solving it? Well, if you churn through, I'm not going to bore you with all the details right here, but if you churn through all of the details, your desired R1 ends up being equal to 2 times P in over Q in minus R0, and your desired R2 ends up being equal to 2 P in over Q in minus 3 R naught, if I'm reading my notes correctly. So we end up being able to get R1 and R2 entirely in terms of known desired problem parameters. So hopefully you found this example problem interesting and compelling. If you're ever designing bioreactors, you got to very carefully control your flow, your fluidic network, in order to make sure if you want desired flow rates. So hopefully you found this interesting. Thanks for your attention, and good luck with your study of fluid mechanics. Cheers.